guys, a very happy morning to all of you. And guys, now we are just going to start the next lecture in the manufacturing technology, especially in the welding chapter. In the before chapter, I just concluded. It means I just told a little bit of extra information about the welding. So now we'll just get started about the remaining extra kind of information. Okay, without wasting time, let us get started. So mostly I will try to cover the entire theory subject at first of all, and after covering the entire theory subject, I will just directly go into the problems. Okay. So now we can just start. So first thing you can see. So this is generator, and as well as you can see the power supply is given to the cathode as well as the anode. Okay, here you can see cathode is a positive, means negative charge, and charge with which uses electron, and anode is a positive which accepts the electron. So you can see always the gap should be maintained minimum. Okay, should be maintained. Example, the current goes with means electron only, the most of the current flows. Okay, in positive charge only less percent of the current flows. So maximum flow of current is in an electron. So you can see in next one, the means while giving the current, the electron strikes the workpiece and very hard, and the velocity becomes zero definitely. So while it's been hitting, it will definitely produce large amount of heat there. Okay. Okay, while it's been hitting, it produces a large amount of heat there. And you can see since like if it's been like this, means the welding material won't go downwards. So we take like this and we place the welding material. So now the each and every the welding will go strong. Okay, it will go down good because of the, you can see, because thermal conductivity of the workpiece is so much low, so much high, so that's why heat dissipation occurs more. Okay, you can see only 65% to 70% of the heat is generated at the anode level. Okay, so it means the heat is transferred, and the 65 to 70% only of the heat is transferred. Okay, remaining 25, it means remaining 25% to 35% heat is at the cathode. So you can see this is straight polarity. Okay, so there is straight polarity, there's a reverse polarity, we'll just see. Okay, so next thing is you can see thermoionic emission, means by giving heat the electron is removed. Okay, by giving heat the electron is removed from the material. Okay, thermoionic. So next one is field emission. You can see electrons comes out by the electricity, and second emission you can see as electron comes out from the cathode, strikes the air molecule, and from the air molecule see the electron. Oh wow, I think you are getting the point. So next one you can see tungsten. Tungsten is a cathode spot is fixed, and you can see aluminum and magnesium cathode spot goes, it means cathode spot goes here, and definitely. So generally guys, because if I just show you any kind of examples, means you can have a clear cut understanding. So we can just see how the entire welding process works. So you can see this one, this is electrode, and this is a image. You can see whenever there is an interaction between positive and negative charge, definitely the spark will there. So you can see the spark will be created. You can see this is the cathode spot, and after this cathode spot, each and every ions, it means positive and negative ion, will get separated, and you can see this entire thing is to a plasma state. Okay, you can see cathode top is in, and at the bottom there is an anode spot. Okay, cathode spot will be top, and the anode spot will be in the bottom. But anode surface is so good. Oh, this is not this is just a workpiece. Okay, it means positive ions goes up and negative ions comes up. So but both will not intersect. Okay, this is most important because it's plasma. So generally plasma state will be positive and negative charge will be separated so much. Okay, so next one you can see cathode spot, where the voltage is definitely at this kind of cathode spot, the huge amount of voltage drop will occur. So that's the most important thing. Okay, so you can see this one, this entire thing. So you can see this spot, it means this is the graph. Okay, the anode spot will be down and the cathode spot will be the top portion. So while it's been decreasing, you can see the entire voltage at the beginning will be high, and later on it will just go on decrease. Okay, so you can see power equal to, it means voltage of cathode, voltage of the total power, and voltage of anode into I. Okay, so power is V into I. It means voltage is I just about, so V equal to IR. Okay, I think so you know, it means you already know the concept. So it's as per, and the energy equal to VT into, it means voltage power into time. Okay, that's it. So energy equal to I square RT. Okay, so you can see this one. So this one is explain. Next thing you can see AC is not continuous or gas definitely, but DC is a continuous, so you can go continuous. And non-consumable electrode is stick. It means tungsten inner gas, and carbon inner gas will also comes in non-consumable. And consumables, you can see this is MIG. So MIG is it means metal inner gas welding, and no name at first. Metal, it means whenever it means a thing is not given any kind of name, means it goes in the category of consumable welding. If any tungsten, carbon, aluminium like this, if it means it is non-consumable. So that's it. Okay. So next one you can see DC arc welding maintains stable. Yes, definitely DC arc welding maintains stable arc and preferred for difficult tasks for over. Okay. So there are three types of mold. It means metal transfer. So it means one is global transfer, next one is spray transfer, the next one is short circuit transfer. So in this it means the extra addition thing is it means straight polarity direct welding, and next one is reverse polarity direct welding. So mostly in the welding process we use kind of direct, it means direct only. So what it means AC we are using the DC only. So you can see work material heated moves faster than electrode. Yes, definitely. It means straight polarity and deeper penetration. Yes, less electrode consumption. Yes, definitely. Okay. So let's deposition and a narrow shear heat event, and this is preferred all metal except aluminum, magnesium, and copper and beryllium. So straight polarity is generally used for most of the material except aluminum, beryllium, copper, aluminum, beryllium, copper and magnesium. So next one you can see reverse polarity. So in this reverse polarity, the entire workpiece is negative, and if the workpiece is aluminum, so it is, yes, definitely the workpiece is negative, because the electrons tends to come out of the workpiece. Means what will happen, it will just remove most of the oxide that is being present in the outer layer. So it will remove the outside oxide. Okay, that's it. So you can see, because the system has a innate ability to scatter the oxide films from the surface of the work, it will is very useful for welding aluminum as well as magnesium. Okay, so where oxides are very much hard and brittle, so when any kind of, for most of the brittle material, reverse polarity is generally used. Okay, reverse polarity direct current is used. Okay, so the type of welding prefers clean surface, electron consumption faster than it means electron is definitely, and preferred in thin sections. Electron flows from workpiece and will tend to clean the surface, and use, it means used for non-ferrous metal. Okay, non-ferrous metal, not ferrous metal, there was non-ferrous metal. The next one is there are three, it means three modes of mole transfer during arc welding. You can see this globular, spray and short circuit. Okay, you can see metal transfer from the electron to workpiece. Okay, it means spray transfer means just, I think so you will have seen the barber shop, they will just spray, so like that the spray and circuit. So molten metal droplets, it means this is the electrode guys. Okay, there it means sometimes the electrode also goes in a huge bulk way, and sometimes the droplets, and sometimes the spray way also. So molten metal droplets from electrode to well dark at rate of several hundred droplets per second. Yes, definitely. And you can see spatter is, spatter prevents, it will be very much stable. So you can see drop, so it means spatter means it's like a splashing. It means when you just drop it means water, it means a drop of water, it just spatters, it means it just spreads around. So drop around leads to splashing of material. It means, okay, so big droplets is definitely, big droplets means the more spatter, so smaller droplet less amount of spatter will be. So this type is very stable, and high DC current, it means more current, it means you can see more roping of electrode. So larger diameter of arc is used to, so it means generally is to mixture of shielding. So generally guys, each and every welding process is, we will do the argon gas, it means surrounding is being surrounded by shielding gas. Okay, so this is kind of spray transfer. Okay, so in the spray transfer generally the shielding gas is used. Okay, and this type of arc is very much stable, so high DC current, more current. Okay, large electrode are used with the argon shielding gas. Okay, next thing you can see, it means carbon dioxide rich gas are utilized. Yes, definitely for global transfer, it means surrounding. So next one is considerable spatter. So spatter will be little bit. Okay, so I think so. The next one is high current being used. Okay, definitely high current being used. So penetration is so much high in the global transfer. Okay, and high welding speed and more than spray transfer. Okay, heavier sections are completely joined by separately. Definitely. Okay. So next one is generally short circuiting. So mostly the due to the short circuiting, a lot of transfer is occur. Okay, you can see current transfer is only 200 ampere, but while short circuit comes, it goes to 2000 amperes. Okay, so because of the voltage drop as well as the pressure drop, it means the current drop. At this huge amount, it means at this huge current transfer, it means a dropper will be used, power supply, so cuts the current and stops the process. At this time there may be huge metal transfer, and it may happen for just 1 millisecond. So huge current flows for 1 millisecond, huge metal transfer. So that is called short circuiting. So due to the short circuiting, we are just transferring lot of, it means lot of materials within a short duration of time. So electrode tip touches the workpiece. Okay, individual workpiece. Okay, this electrode tip touches the workpiece. So you can see forces which takes place in the metal transfer is gravity force, surface tension force, electromagnetic force, hydro action, atomic hydro action, hydrodynamic action of plasma. Okay, I think so are getting the one. So overhead wheeling. So next one is this one. Okay, so these are the just an extra thing that I just wanted to tell you to. it's perfect. Wait, this one, okay. Oh, now it's okay. So you can see this one. So it means arc welding equipments. First one, drop power supply to maintain. It means maintain constant current. Okay, welding machine. So good for manual welding. So generally CM. It means CM means what? Constant current used for manual welding. Constant current, guys. Okay, constant current is generally used for manual welding. Okay, why manual means because sometimes the hand may shake. So this kind of, due to a little bit of extra problems, this kind of manual welding is being used. Okay, you can see this one is constant current and this one is voltage with respect to I. So you can see this is constant current. You can see the current is so much constant, but you can see the voltage is being dropping. Okay, so this constant current, you can see from here to here the voltage is being dropped. Okay, we are just going and taking like this. Okay, for the constant voltage means the voltage will be like this, and you can see the current will be dropping like this. Okay, and these are getting the points. So next one you can see constant voltage machine. So constant voltage machine is generally used for robots. Okay, so generally 220, most of the heavy volt we won't give, we only will give so much amount of short voltage. Okay, so you can see this one, but generally 110 volt only we are just giving, and you can see wire bigger and it means, and also why, because suppose if we use 220 volt means definitely the material cost and each and every cost will be so much high, so that's why we reduce. So next one is, you can see about this one. So this is also one of the important graph. Okay, so this is, you can see it means this voltage, this current. So this is OCV, this is SCC. So you will just connect this one. Okay, you can see at this maximum voltage you can see zero current, at this minimum voltage it means at this maximum current there is zero voltage. So at the center we will just get the maximum. Okay, so what is the area? It means what is the, it means curve, it means straight line formula. So I divided by SCC plus of V divided by OCV equal to 1. Okay, I divided by SCC plus V divided by OCC equal to 1. Okay, I think so you are getting the point. So this is the equation of straight line. Okay, this side SCC, it is current, short circuit current, this is open circuit voltage. Okay, so it means OCV, open voltage there and no current is voltage, and battery keeping normal. Okay, short circuit current flows, voltage drop. Okay, so I think so I can able to understand. So what is the, it means maximum power? How we can just calculate the maximum power? It's so simple. You can see this power equal to voltage into I. So okay, we will just turn one side this side. Okay, for example we will just turn, it means V equal to 1 minus of I divided by SCC of OCB. Okay, now we just multiply the OCB inside. It means then this is entire voltage thing. So you just multiply this kind of thing into I. P equal to 1 minus I divided by SCC OCB into of I. Okay, now we will just directly get the I and each and everything. So what is the value? I will come, I equal to SCC divided by 2 and V equal to OCV divided by 2. So I think so at this midpoint we will just get the maximum. Okay, so power maximum equal to SCC divided by 2 into OCV divided by 2. So power maximum equal to SCC into OCC divided by 4. Okay, so these are the extra questions there. So next one is, this is also one of the most important thing, guys. So melting efficiency we need to calculate, because you can see to weld the material total power equal to voltage into I. Okay, voltage into current. So you can see this one is the total voltage that we are just having in our hands. So okay, it means at this step it's about 50,000. This means it's going to weld certain kind of material. Okay, while this entire heat has been transferred, you can see it means here 70% will come, and to the top of the above 20% will come, and to the surrounding 10% will just go out. Okay, but we had how much, 100%, but now we are just having only 70 to 80%. So within that 70 to 80%, how we are just going to calculate and each and everything? Let us see. You can see it means in the 50,000 only 20,000, it means heat loss due to heat dissipation. Suppose it is 70,000, remaining is 30,000. So this 30,000 is used to goes to melt the metal as well as to heat the metal. I think so. You would have learned about pre and post. This kind of thing. This kind of 30,000 will just do. Okay, you can see metal means workpiece and electrode. Okay, metal means workpiece as well as electrode. And electrode melts more. You can see electrode melts more means it will just go and hit the workpiece so much harder. And you can see workpiece also means but lesser version. So this one electrode. Okay. I think so you can understand this one. Okay. So next is what is the amount of total heat used to melt the entire thing. So total heat equal to m Cp delta T plus of m into latent heat. Okay, that's it. So not a bigger it means bigger complicated thing. It's such a simple thing only, m Cp delta T and into m of L. Okay. So sometimes if they ask any kind of kg per second or just put that, that's it. Okay, next one is metal deposition rate. Metal deposition rate. So why the metal deposition rate is? I'm just joining this kind of two steps. So here the metal should be deposited. Okay, so metal deposition equal to millimeter cube divided by second. So area into velocity. It means this is millimeter cube millimeter per second. This is millimeter square. Okay, area into velocity deposition rate. Okay. Guys, sometimes you should not get confused. You can see sometimes metal deposition rate is given, sometimes mass deposition rate is given. So we have to have a clear picture in our mind. Okay. So next you can see this 30,000 is goes to melting the metal equal. What's of melting equal to 20,000 and remaining 10,000. It means only melting is used for. So remaining is remaining kind of extra thing. It means loss due to conduction. Okay. So you can see total melting efficiency equal to Hm divided by Ht. Okay. So you can see about this. You can see calculate electrical power P equal to VA and calculate heat transfer is equal to VA divided by heat efficiency and modulus can calculate my use metal deposit MO this metal deposit and heat required to fill the molding. So HM equal to MCP delta D plus or CJ D. So you can see heat required for melting. So how much amount of heat is required for melting the entire volume? Okay, so it means millimeter cube divided by second equal to heat is joule per above square. So whatever this much amount of joule of energy if any means you can just calculate as it is easy. Okay, melting efficiency how much melting heat melting how much heat input per H divided by V. You can see then for 1 mm how much heat we are needed. This is 1000 joule per second. What so tell for 5 mm per 1 second and then 1 mm we must not even know what the energy. Okay, next one is duty cycle. So duty cycle is the person who is getting to be built for next 5 minutes. Okay, next 5 minutes. Yeah, now he needs to be clear the campus. Next 2 minutes after 2 minutes. So next one welding efficiency continue. It means how much. It means time required to build total of minutes. Okay. The percentage of the time is second. So the percentage of the time is semi-periodic. Okay. So you can see the percentage of the time in 5 period, that is welding machine can do. It means the time operating is so much good. So setting time, machining time and the welding time, each and every time is being considered in the duty cycle. You can see required for formal welding 60% or 60%, for automatic welding only 100% is used. So you can see required duty cycle. Required duty cycle TA equal to T divided T not equal to 2 not. So TA equal to I divided by IA whole square of T. Okay, T is rated duty cycle, I is rated current. Okay, so F naught is the maximum current at whole cycle due to variable. So these are the extra things. So next one you can just see about the electrodes. So we are just going to see about the electrodes. You can see electrodes comes under two: non-consumable electrode and consumable electrode. If metal means it can be, it means if metal is there, it means in the name means it is non-consumable electrode. For example, if the name is given tungsten carbide, means it is non-consumable electrode. If a name is not given, it is consumable electrode. Okay. You can see non-consumable electrode made up of carbon, graphite and tungsten, and carbon graphite used in direct current. Okay. Next one, electrode not consumed. Yes, definitely it's the most important thing. Electrode here, the entire thing is not consumed and the arc length is so much constant. Okay, next one you can see consumable electrode. Suppose I'll just show you a video. Non-consumable electrode welding. Okay, I think so. You can see this one in this tungsten gas welding is non-consumable electrode. Okay, you can see in this the electrode will not be consumed. I'll just show you perfect. So you can see here. So you can see here the entire thing is been, this is a metal and this is a, it means a rod. Okay, in this the entire the tungsten electrode will not be used. Okay, it will be so much stable and each and everything will be so much better and entirely direct current will be used. Okay, so you can see straight polarity. So generally it means for AC current we are not using straight polarity only, sometimes mostly we are just using. So I think so you are catching the points. So you can see this one. So it's they're using the, so you can see the welding process been making. So from here the welding process is been making. Okay, see how much perfect is that. Okay, So you can see the entire thing. Wow. I think so you're getting the point, guys. So simple. You can see non-consuming electrode made up of carbon, graphite and oxygen, and carbon and graphite using direct current. And electrode not consumed, yes, the electrode is non-consumed, and it means arc under so much constant, arc is stable and easy to maintain. Consuming electrode, you can see, provides filler metals and the same composition and experience welder welding, yes, definitely. So three kinds: base and fluxed, or lightly coated and extruded. So for automatic welding, bare electrode is in a form of continuous wire. Okay. For automatic welding, so bare electrode is form of continuous wire. Okay. So you can see, since coating is provided while bending, the coating may be break, okay, and fall. So like this, you can see it's been continuous, so it may be frog. So this is a problem in automatic welding. Okay. The next thing you can see, it means just wait one sec. Okay. So the next thing, you can see electrode coating characteristics. So provides electrode coating as electrode must be coated. You can see provide protective atmosphere, stabilize the arc, provides a protective slag coating to the accumulated impurities and prevents oxidation and slow the cooling, as definitely, and reduces spatters, as definitely, and adding alloying elements, yes. Arc penetration is good, because while we are just feeling arc penetration is good, and influences the shape of the weld feed and adds filler rate. Okay. Next one is arc stabilizing ingredients. So air is not sufficient conductive to provide stable arc. So we add some of the materials to the coating, so it acts as a truss and provides a stable arc. So example, titanium components, potassium components, calcium components, potassium silicate, potassium oxalate, zirconium carbonate and lithium carbonate, titanium oxide, and lot of extra things we are just adding here. And next you can see flux and slag forming ingredients. So these ingredients are used primarily to improve properties such as slag viscosity, yes, definitely, because flux and slag we are just using some of other ingredients also we just add because to improve the viscosity, because while the filler material is been flowing so much easily, means definitely the viscosity should be good, and surface tension and melting plus also should be good. Okay. So you can see slag is asbestos, silica, fluorospar and iron oxide. So magnesium, aluminum oxide, titanium oxide and rutile, this kind of thing has been used. Okay. So I suppose for your case I just asked you this thing also, you can see here. Why we are adding slag and other kind of extra elements to the welding electrode coating materials? So tell me the materials to improve slag viscosity, surface tension and melting point for the electrodes. So you can see, I'm just asking to chat, you can see. So slag formation, slag, and the other thing is slag covers the molten metal and protects it from oxidation and as well as nitrogen absorption. And you can see R stabilizes certain oxides and carbonates stabilize definitely. Control of, you can see viscosity, surface tension and melting property of the slag based on bead shape. Okay, according to the bead shape, each and everything is been showing here. Okay, I think so you're getting up. So you can see silicon oxide, alumina rises viscosity, reduces slagless fluid, and magnesium oxide also contribute to higher viscosity. Calcium chloride and titanium dioxide, you can see, reduces surface tension and gives smooth feel. Okay, titanium, it means neutral, TaO2. Titanium dioxide is TaO2. Okay, next one is calcium fluoride, lower surface tension. So it means suppose for your understand why surface tension, viscosity and melting point is important in this. So you can see why it means why we need the surface tension. You can see control bead size. Low surface tension allows a molten metal to spread easily. Okay, so surface tension is lesser means we are able to spread the bead so much quickly and so quickly. Okay, so you can see influences wetting of base metal, better fusion between the base and filler, and affects slag detachability. Okay, right balance ensures slag peel off cleanly after solidification. If too high, it means if the surface tension is too high, weld metal piles up under poor penetration. If too low, weld doesn't spread. So okay, why the viscosity important? Because the viscosity tells how each and everything should cover. Okay, so you can see under proper viscosity ensures slag and it means it also provides against air. Okay, the next thing you can see R stability. Too viscous sludgy slag and traps the gas bubbles. Okay, that's why it means this also leads to porosity also. So that's why each and everything is important. Okay, so next thing, if it is lesser viscous means also a problem, and balanced viscous we just need. An important melting point because timing of slag product, because slag must melt before. If the slag doesn't melt, it also is a lot of complicated. If slag melts too easily, very low melting point, it becomes too fluid and runs off. Okay, so that's why each and everything is so much important. So okay, next thing you can just see about this one. So deoxidizing ingredient, you can see why it means sometimes the oxygen also gets infiltrated into the the material. So we can't remove 100% of oxygen. So 99% we can just remove, but 1% will be still remain inside. Okay, so for that purpose we will use ferro silicon ferro sorry for my editing ferrochromium. Okay, ferrosilica, ferrochromium, magnesium. Okay, so while we are using ferrosilicon, you can see this reacts with 1% of oxygen, and it means this silicon attracts the O2 and it will come outside. So you can see Fe goes to the workpiece. Okay, so and you may have a question why we can't use the silicon directly, because we can't use the silicon because it can't penetrate easily, so we add ferrosilicon. Okay, next one is binding material. Binding material like adhesive force. Function of binders are to form plastic mass of the coating material and capable of being extruded and bakers. You can see binders are used for making coating non-flammable to avoid a premature decomposition. First of all, I'll just explain this one. So you can see this one, rutile electrode. You can see the resin and titanium oxide rutile. So surface tension low, wheel pulls sweat easily and smooth flow. Viscosity low to medium, slag flows easily and uniform cover. Okay, melting point of the slag moderate to low, slag melts quickly and covers them. Okay, beautiful bead shape. Okay, next one is basic electrode. You can see calcium carbonate and calcium fluorospar. You can see surface tension high. Weld spread. You can see since surface tension is so high, weld spread is so much lesser, and the deeper penetration and stronger joint we can apply. Okay. And the next thing you can see viscosity is high. Okay, slag is thicker and holds weld pool stable. Wow. And control solidification. Melting point of slag is high. Slag forms better and solidifies. I think so you are able to understand this one. So first we will just ask this one. Okay, why the binding material is important in the welding? So tell me about sodium and potassium silicate electrode coating in binders. So binding material because it used to join of the two kind of forces. Okay, you can see function of binder is to form plastic mass of coating material capable of being extruded and baked. Binders are used to making coating non-flammable and to avoid premature decomposition. Okay, sodium and potassium silicate electrode coating in binder. Okay, so you can see it means why binding material, the coating electrode has many powder, slag and everything. This powder can't stick to the electrode wire. Yes, definitely the powder can't stick to the electrode wire. That's why binder hold. You can see holding the coating together keeps in all in a frame and provides ionic conduction. During the welding, binder decomposes and releases ion that stabilizes the work and control moisture content. Okay, binder chemistry also observe how the water is absorbed and affects burns of ratio, influence how coating melts and feeds into the orchestra. So you can see sodium silicate. Sodium silicate has binder strong binding and cheap, and you can see sodium ions in the as each and everything here DC only has need to be good. You can see potassium silicate, potassium ions are better. Is it okay? I think so you're able to understand. So the next thing you can see here, it means we used to improve the strength of welds and magnesium and this kind of other element we are just studying. You can see titanium oxide and potassium our components increases the melting rate of base metal and better penetration. Okay, so iron powder provides higher decompression. So generally this kind of thing they generally don't ask, but you have to just know it, that's it. So you can see plasticizer. So coating are often very granular and sandy. In order to successfully extrude the coating, it is necessary to have lubricating material. Okay, so that's why plasticity is means to make the coating flow smoothly under pressure. Okay, next one, gas forming. So we use cellulose and carbonate as Ca and magnesium, is calcium and magnesium in welding. While burning this, CO2 and CO and H2O are formed coming out. The gas prevents the reaction with O2 with the workpiece. So this gas provides a protected atmosphere. Free moisture is another gas forming ingredient that is formed cellulose type electrode. Okay, free moisture. Slag is chipped and coating are designed to melt more and slowly than the filament. So next one you can see binders. So generally you can see AC binders. AC welding use potassium silicate binders, and for DC we are using sodium silicate binder. Potassium has low ionization potential as compared to sodium. So ionization potential you can see means when potential voltage the ions of the electrons, it means for example at the beginning, it means for example if you just start the car at the instant, also at the instant it is so much difficult. First it have to just push the weight of the car. It means the engine's force should need to push the weight of the car, later only it have the capability to move. Okay, it means that's called ionization. Until a certain limit only, after the ionization potential will act. So you can see potassium has less ionization potential, so voltage less, the flow can be so much good. Okay, sodium has highest potential, so voltage we need to supply lot and lot. Okay, I think so you're able to understand. Okay, this one we just cover. You can see as I just told, welding flux all are all in one. Okay, that's it. So granular electrode wire coating and electrode coat, and you can see granular generally is powder put on the workpiece up. Okay, and after weld. So I'll just tell it means I'll just show the video later on. And you can see electrode core, it means it means this is an electrode core. You can see hollow electrode, inside we will the flux material is filled. Okay, this is entire thing is electrode, means the inside will just build the powder, and electrode wire coating electrode. Okay, so this, it means this entire thing is electrode core flux core. So what is the difference between ABC? You can see A and C, it means granular electrode, so electrode wire coating and wire. So flux material are provided outside. Okay, flux material are providing outside, which lead to absorption of moisture definitely. While the welding at higher temperature, H2O and H2O becomes again and defects occur in the workpiece. So that's why we are just providing the flux inside the electrode. Okay, in industry we use C. This electrode wire coating welding we use. So but always we will just keep in the furnace and heat them. At the time of welding they will just bring out and we will do the welding kind of thing. Okay, I think so you're getting the point. So generally you can see they will keep at the higher temperature. So low electrode, high tension. Okay, that's it. So you can see welding position flat, vertical, horizontal, and over. Okay, these are just normal thing. And this one also sometimes they usually ask in the questions. So you can see welding current I equal to K into D. Okay, it means D is diameter of electrode, K into D, and the voltage welding voltage is P equal to K1 plus of K2 of L. Okay, equal to K1 plus of K2 of L. Okay, so L is arc length, K1 K2 are constant. Okay, so next one is you can see arc length. For good weld, a short arc length is important, not social but medium. Okay, because arc length tells each and everything. You can see heat is concentrated, more stable, more protective atmosphere. So you can see if it means a longer arc is there. This is the electrode, and you can see this is the workpiece. Longer arc is there means heat loss is more. Unstable arc, wheel to pull is not protected. Weld, it means each and everything will be in a problematic thing. Okay, so if a good weld need to occur, means you can see arc length equal to diameter of electrode size. Okay, arc length must be equal to diameter of electrode size. And bead width, you can see this one, if the thing is melted, means bead width, this width should be equal to 3 times of diameter of electrode. 3 times of diameter of electrode. Okay, I think so you are able to see, understand this one. Okay, we'll just cover this one. So next one you can see arc blowing DC arc welding. Okay, So generally, mostly while suppose if you just match stick, and if you just blow means definitely the fire will just oscillate here and there. So same like that, arc blow will also occur in the welding. Okay, so you can see this one, it means this side is being connected to positive and the entire workpiece is connected to the negative. You can see here it means like this, it is been there means the transfer of electron here and here it will occur so much quickly. But whenever the electrode is been passing here, you can see the transfer of electron from here to here it should occur. Okay, so this is called as arc blow. So like this kind of arc blow, the stability, it means the arc won't be that much stable. Okay, so I'll just show you. So but anyways, I'm not getting the thing. Okay, so you can see, suppose for example, instead of going in a straight way, it is just going to like this. So okay, so I just told about the powder spins, for example, the it means the granule, the powder electrode. So you can see the entire granule flux will be poured over, and later on we will just do each and kind of the welding process. Okay, I think so you're getting the point. So you can see this is kind of arc flow. So that's why we used to place the, it means the charges here. So you can see it happens due to the unbalanced magnetic field lines. Okay, so you can see arc flow occurs during the welding of magnetic material with DC. So if we use magnetic material with DC, definitely this kind of arc flow will occur. If the workpiece is not magnetic, so no magnetic field will produce. Okay, the effect of arc flow is maximum when the welding is at corner and when the magnetic field concentration is maximum. Electrode may be magnetic or not, but the coating is always non-magnetic. Yes, definitely this. So sometimes the coating is always non-magnetic. Okay, so higher magnetic field nickel ion. Okay, higher magnetic field nickel alloy causes strong magnetic field in metal and more unbalanced magnetic field. Okay, it means high magnetic field nickel alloy causes strong magnetic field in metal. Okay, more unbalanced magnetic field. So this effect is called, this effect is known why we are using bare electrode. Okay, while we are using bare electrode. So you can see next one, effect of arc flow. You can see low heat penetration and excessive weld spatter. Okay, arc not flow at the exact location, it goes to some other location. Low heat penetration. Okay, instead of going here, it goes here. So excessive, you can see excessive weld spatter occurs here. So next one is also occurring pinch effect. It means electrode sticks to the workpiece. This is because of sometimes electrode sticks to the workpiece because of electromagnetic force. This is called as pinch effect. Okay, so weld spatter occurs high welding current and too small electrode arc. Okay, we minimize them by shortening the arc. Okay, reducing current, reducing weld speed, balancing magnetic field by placing the at one end of electrode. Okay, wrapping the electrode cable wire in terms of, so like this. Suppose while we are just wrapping this kind of thing, definitely the electrode, it means the electrode arc, arc doesn't occur. Okay, guys, that's it for this video, and I'll just see you in the tomorrow's video. And in tomorrow's video, it means we will just try to cover mostly the entire chapter quickly. Okay, one, two, three. So mostly, definitely, in my guess, and the theory will be extra 3 classes, I think so, and mostly the problems will be in extra 3 classes. So within 6 classes, I'll just try to cover the entire welding chapter. Okay guys, that's it for today's video, and let me see you in the next video. Until then, take care, bye bye.